Welcome everyone, it's my pleasure to introduce Rene Mboro from here at the University of Miami. He will speak about basic remarks on Lagrangian Submanifolds of Hyper-Kaehler Manifolds. Please,
So I will start with myself what Hyper-Kaehler Manifolds are. So Hyper-Kaehler. I will just write HK for the rest of the talk. It is simply connected. And is that the space of automatic forms is generated by just one symplectic form. Of course, they are quick. Because it has a symplectic form, the dimension has to be even. And another quick consequence of the fact that there is a symplectic form is that the canonical bundle has to be free. It is nowhere vanishing, so when you take the nth power, it gives you an holomorphic form of so, and those manifolds are very interesting, usually because there are many reasons for that. One reason, for example, the completion theorem to Fourier. That says that this M is a compact manifold, complex manifold with trivial shared class. Then there is a finite state cover. Such that M can be written as the product of the complex torus the product of Hyper-Kaehler manifolds and the product of Calabi-Yau. Yeah. Hyper-Kaehler are one of the building blocks of manifold with trivial shared class. So this is one reason. Another reason is like they are a natural generalization of one of the natural generalization of characteristic surfaces. So I mean, of course, you have two ways to generalize characteristic surfaces. You can write them as I just remind that you have trivial canonical class and so on, then you can end up with Calabi-Yau manifold. But when you insist on having a symplectic form, then you get this class of Hyper-Kaehler manifold. So I mentioned K3 already quite some time, so let me give some examples of those to be quick. So in dimension 2, the only kind of Hyper-Kaehler that we get are K-free surfaces. So in higher dimension, we have the example given by Boville. So if we start with the first kind of example, start with S, a K-free surface, and we look at the invert scheme of length and zero-dimensional subspace. So this, by work of Fogarty, is smooth for any surface, and so actually the fundamental group of such a thing can be computed also with a little bit of work. So for n at least 2 fundamental group of this. So you take take a point inside here. For example, you take a pairwise distinct point. For sure, they give you a length and subscheme. This is H1 S. So in our case, starting with a K3, it is 0. So this is generally for any surface. It is 0, so you have that it is simply connected. And for the symplectic form, what you do is like there is a natural map, rational map like this, we call it F. So you have to, and the idea is that the symplectic form to the scheme is when you pull back to the just product, you take the sum of the symplectic forms on the K3. So this is one example. Another example given by Boville, that we start with an Lagrangian surface. Or a complex torus of dimension 2. Not related that. And we look at, we take again the length n+1 subscheme, but here we have we can do some things like can take the sum. Yes, so we for length n+1 subscheme, we just focus on the support, and then with the multiplicity, and then we sum them with the addition law of A. So we have a map like this, which is surjective, which is A equivariant. So all the fibers are isomorphic, and by this we see that it is not simple. This is not simply connected. This is not simply connected, of course, and they have the same phi 1. So what will be simply connected? So this is a fibration. So what will be simply connected is the fiber. So this is called generalized Kummer. This is so this is simply connected, and you can also check that there is a symplectic form. Then you have some examples in dimension 6 and 10, built by O'Grady, as this angularization of definition of some moduli space of sheaves. So here it is on the ambient surface. Here it is on the K3. And of course, so those are examples that you can then deform them and get manifolds that will not be exactly the dense subscheme of the K3, but just a deformation equivalent to this thing, and the same for Kummer, the same for other examples, and so on. So, and so we have first object, Hyper-Kaehler, and then we have the second object of the top.
And those are all the known examples, I mean, with the deformation classes.
Yes, yes. For the time being. For example, in the case of Grady 10, there have been people like Gunnar, for example, Sanka, that have found something. Another way to build an Hyper-Kaehler which is deformation equivalent to this one, but using geometry. You need geometry of so what they do is they start with a cubic form, and then they can look at hyperfluid sections of this. So this is a cubic threefold, and in the cubic threefold, what you can look at is the intermediate Jacobian. And you put them in family. So say you stick the locus where those hyperplane intersection are smooth, then you have the vibration like this, and you can prove that this is an integrable system, and then they work to compactify it over P5 and check that you can extend the symplectic form and so on. So say that maybe using geometry, maybe in other cases, maybe you can, if you have such setting, similar maybe in higher dimension, it might come on something genuinely new.
The expectation is in large dimensions, is what you.
So where is the hope? Where is the
Oh, I don't know.
which dimension? Lower?
Larger than coming from. The lower may have this kind of sporadic one. The larger.
So,
All examples are pretty old.
My Hyper-Kaehler was 1 X, so it's a submanifold. The n-dimensional submanifold. The full back of the multi-fold dimension. So, examples we have. So, of course, we have curves on K3, just because the symplectic form on the one-dimensional space has to vanish. And then we have something. You have abelian varieties that come and a very nice theorem of mathematics. start with a Hyper-Kaehler. And we assume that there is a morphism to the variety B, which is normal projective, and dimension strictless. So then, this thing is more rigid than we might have thought. So what we get is that B has to be half the dimension of Y. It has to be might be singular. Not to say. I don't state exactly the meaning. So the canonical has to be anti-ample. And what else? The Picard rank has to be 1 of the base. And F has to be, oh, so sorry, I forgot. So we have this with connected fiber, general fiber. So just the general fiber. Then F has to be flat, and all the fibers have to be connected. Are connected. And Lagrangian. So for the smooth one, you know what we are saying, and for the singular one, we take the desynchronization of one component and you put back the selected form to the Lagrangian, and the smooth moreover the general fiber is an abelian surface with a variety, sorry. Dimension n. So
wasn't there some condition like smoothness or something which makes B n?
yes. So the conjecture here is that B should be Pn. So there is a case proved by one. What you are saying, if B is smooth, then B is Pn. And there is another case by Oibrecht and Shu. So for if the dimension for Hyper-Kaehler fourfold is true, B is P2. But I mean, in general, yes, and so you can give some other examples of. So we have seen curves, we have seen abelian varieties, and what we can again, if we take, for example, a curve on the K3. Then the symmetric product sits inside the Hilbert scheme, naturally. And if you remember the description of the symplectic form, you have to use the symplectic form on S to build it. You will see quickly that this is Lagrangian. For example, if you have a P1 inside the K3, then it tells you that the symmetrical product of P1 is the same as N. The Lagrangian subvariety. You can have a very similar example. So, example, if you take C1, C2 in a K3, that lifting transversally. Then the blow up of the intersection embeds into the inner square of S as a Lagrangian submanifold. So something which doesn't come so obviously from K3, if we take cubic fourfold, then by work of Boville and Donaghy, the variety of lines on Y is a Hyper-Kaehler fourfold. And by work of Voisin, if X is a smooth Hyper-Kaehler section, then the variety of lines on X sits inside this Hyper-Kaehler as a Lagrangian submanifold. So we see that it can be, so here it is a rational variety, here it is a variety, I mean, if C is of genus at least 2, this is of general type, and so on. This is a surface of general type, and so on can have many different, maybe they can, yeah, there is how to say, so you use skepticism that you are not only working with curves or and that
Is it known for all known examples that they admit this type of morphism in Monticello still?
No,
It's not known.
Usually in the moduli space of Hyper-Kaehler, it's only on the divisor that you have the.
I mean, up to the formation, I agree. Or is not known.
This I think is I don't think it is known. I mean, of course we know that the if you start with one that has Lagrangian fibration, then you have a hyper surface, but whether
the form 1-to-1 which has another.
Exactly, I don't think it is known. So now we can ask ourselves, so we have this nice kind of object like Lagrangian fibration, and we can ask ourselves how other Lagrangian manifolds interact with this thing. So this is so I discovered recently that something that so what we say that simply observe the Lagrangian vibration of the Hyper-Kaehler manifold, and take X submanifold such that the projection doesn't lie entirely in the discriminant locus. Then so if I denote the restriction X, then the general fiber of F is a union of ambient subvarieties that are deduced one from the other by translations. So with this hypothesis, the general fiber, you have we see the so
Why is that Hyper-Kaehler?
why is that Hyper-Kaehler? Yes. I gave a proof of this fact when you have a section, but I discovered recently that actually in a paper about special Kaehler manifold that Kamenova and Gavsky gave a proof about this additional assumption. So actually the proof is quite simple. So let's start with this lemma linear algebra. So if we have the Lagrangian subspace of this endowed with the natural symplectic form. Then so when you take the orthogonal of the projection of D, so the first projection, when you take the orthogonal of this projection, what we find is when you look at the annulus of those vectors here, so the annulator is found here, we find just the intersection. So this is easy to prove. You just coordinate and you show it. Now, in our case, in our case, if we take point, let E be a point of the basis of outside the discriminant locus, and you also take B to be a regular for F. Regular diagonal. F, so it means that the fiber of F over B is smooth, and because you avoid the locus factor of pi is also smooth of the right dimension and so on. So what we get is that first, symplectic form identifies the tangent space, the zone of the tangent space at any point, at any x inside this abelian variety. We have this YB with the obvious meaning. This is the fiber. This is just because we have the Lagrangian vibration, so YB is Lagrangian, and you get that. And then we just have to apply the lemma. So, apply the lemma, so we have now so for now x inside the fiber of the fiber of F. Now we get this. So this is Lagrangian inside this. So this can be decomposed as tangent space T plus this. And this is the dual. So by the lemma we get that this is down upright pi. The eigenvector of this is equal to the intersection So since we are on the locus where everything is smooth and so on, this is just the tangent space to the fiber. Thanks. And we are on the locus where we have regular value and so on. This is just the tangent space to the variety downstairs. And then we have to remind, so we have this. And then we have to remember that we have here an abelian variety, so the tangent bundle is trivial. Y is trivial. So what the lemma is telling us is that the position of the tangent space to xb does not depend is somehow constant in the fiber. So it only depends on B, the fiber downstairs. And inside this abelian variety. So it tells us that what we have in the notation, so that xb is a union of abelian subvariety. Associated with if you look at the uniformization, the linear space inside here associated to those abelian subvarieties is the orthogonal of this one. So it tells us that. You can look at what we get where we see examples of this behavior. Let's take, for example, an unrequest surface. So it's a surface that whose universal cover is a K3. So we have and the universal cover is a 2-to-1 étale cover. And this is a K3. Then what we have is that we have we can embed our unrequest surface in the invert square of the K3 that we know to be a Hyper-Kaehler. Just we take to any point, we associate the pair of points lying above this point. So this is Lagrangian embedding. So this is Lagrangian. Just because the unrequest surface has no two forms. So when you put back the two form here, you get 0. So it's Lagrangian. And if we fix now a line bundle on the unrequest surface, giving an elliptic fibration, such that then we can check that this gives us an elliptic fibration of the K3. Now when we go to the invert square,
how do you embed sigma in the square, the global square?
so above each point of sigma, there is 2 points.
Mm-hmm.
And
You also assign the 2 points.
And then, so when you take the invert square, you have a natural. G2 goes from here to the symmetric product. So this is a P1. So this is P2. It gives you a Lagrangian fibration. And what you have is actually, when you restrict this Lagrangian fibration dq to the unrequest surface, you get back to your original get back H, you can check it. And here it's P1, and the diagonal embedding here. And then so you have that the fibers of the restriction are also ambient subvarieties of you can also get examples where you have a union of ambient varieties. It's easy. You take K3, elliptic K3, projecting the elliptic K3. And you take C, so it's 2 on then we have seen that the product of curves are facilitated, for example, so smooth fiber, so above B, of your elliptic fibration here. So we have seen that this is the Lagrangian subvarieties. So the same procedure as here. The elliptic fibration on S gives you an elliptic fibration on the square, and then when you restrict the fibration to this Lagrangian subvarieties, what you get actually is a map that goes like this. D plus if the elliptic fibration was phi of C, so this is just the P1 of the elliptic fibration. So this is inside the symmetric product of phi of C. So this is just a P1. The B just moves the P1 inside. And when you look at the fiber over this P1, P1, sorry, if you get degree C over I1 copies of elliptic curve. So one thing. So of course, in this theorem, when I said that the general fiber is a union of abelian subvarieties, of course, those abelian subvarieties can be points. Of course. The mass can be very finite. So in the general case, what can you say about the base of this new fraction that you get? We can use, for example, the so-called easy addition lemma. So that says it's used by people in irrational geometry. Let's say that if you have F, so projective of closed, projective. What else? Between normal varieties, will be connected by general fiber. It should be sufficient. Then the Kodaira dimension of X is bounded by the dimension of Y plus the Kodaira dimension of the general fiber. So this is the result of irrational geometry. So if we use it in our case, corollary of this theorem is just that so abelian varieties of course have X inside Y and Y without with fibration. Then the dimension of the base is at least the Kodaira dimension. This. So in particular, if X is of general type, this restriction is always generically finite. Yes. is the whole Pn. For the dimension, I think we can say more when the image is not the whole Pn, but so for example, to say more about my expectation is that if I assume the base to be smooth, I have no two form, no one form, sorry. This in the case where X is a surface, we test us that this is a P1. Right? But yeah, I have a proof that from it. So and when the image is the whole Pn, what can we expect to get from such an object? So this is a y, negative y representation. That we go back to the case of curves on K3. So there is an interesting invariant of when you have a smooth curve. Called the gonality of the curve. Minimum degree of the map to P1. And usually it's an indication of how general your curve is in the moduli space. We know that by Noether theory that for the general curve in the moduli space, gonality is of course for genus history. So for genus 2, all the curves are hyper-elliptic, and this minimum degree is 2. The gonality is 2. So so anyway, you have this formula, and usually the rest of the curve for the rest of the curve is but in general, the gonality of the curve is not easy to compute. But we have some results that say that so if S is a K3 with a 6.3 involution. So the quotient is some Enriquez surface. So in this case, then for any curve such as the self-protection is positive, the gonality can be computed. How to say? Is computed by the by one of the elliptic vibration of S. In such a case, S has always elliptic vibration, but there is one of them that can compute the gonality of C. C is equal to E times C for so many features. And there are also other results of the same kind when the Picard lattice of the K3 is copy of the hyperbolic plane, you have similar results. So we can expect that so in higher dimension so the like that and another fail. And somebody else. In the paper, they introduced so-called measures of irrationality. So among them, they for a smooth projective variety, so they introduced this. So which is pretty much like the gonality. So the minimal degree of dominant map to Pn. Because they introduced other measure of irrationality, for example, the connecting tonality, just for minimal degree tonality such that two general points of X can be connected by a curve of tonality C. So there are other examples of measure of irrationality. So why measure of irrationality? For example, here, if the irrationality is 1, obviously X is rational. And here, for example, if the connecting tonality is 1, X is rationally connected. And then in this paper, they computed for hypersurfaces and so on and so on. So we can hope that that there are simple enough conditions on the Hyper-Kaehler that has the Lagrangian fibration. Ensuring that one of the Lagrangian fibration of the ambient Hyper-Kaehler. So actually, that's for any Lagrangian subvariety submanifold X, one of the Lagrangian fibration of the Hyper-Kaehler computes the degree of irrationality of X. I don't know if there is any other. this, but it will be, analogous to what we have for K3, and we give an additional usefulness to Lagrangian fibrations. So
what is the question? I don't know. You're asking me what?
I'm asking if, just like, so in the case of K3, we saw that if you have some additional simple condition, then the gonality of the curve can be computed by an elliptic vibration of the K3. So I read it as there is an elliptic curve such that. So I'm asking if there is something similar to compute the curve irrationality here, because so for example, if X is, as I say, is of general type, this restriction is generally finite. So for sure it gives you such a restriction. So, and the question is that are there conditions such that there is a Lagrangian vibration that will give you exactly this number?
In the case of the K3, can one easily find such existing?
Actually, I have not read the paper yet. I cannot explain exactly.
General fiber what's the type of which gives
Yes. This is the input element here. This is the general fiber.
It's supposed to be elliptic, or no? Okay.
Yes, it's necessarily elliptic because it is so yes, it is elliptic. So I should have said it. And there is not only one elliptic vibration.
Yeah.
You have to work to find one that so.
More questions?
When you have a Hyper-Kaehler space, you have something called crystal space associated with it. I think one of the properties was it's like rationally connected. I mean, the crystal space is non-Kaehler at all. Crystal space.
In the total space.
Yeah, the crystal space, total space is non-Kaehler. But it still is covered by a lot of rational curves. And I think there are some like maybe something like irrationally connected property or so. This is Verbitsky's basic results, which he uses to prove that I mean, probably this paper with Kamil and Verbitsky is also used. I haven't seen it. But if you uses such curves, I don't know, is there any relation with them?
So the crystal space is the fact that the thing that we get from the canonic structure and you have this deformation.
Yes.
So I think I have to use those rational curves that are here.
Yeah. I mean, to see if one can say something about the existence of this type of curves after. I mean, there are many rational curves which you can say.
I think usually I might be mistaken that when you vary your Hyper-Kaehler in the crystal space, you usually lose if you have the Lagrangian subvariety, usually lose it. Usually sitting one fiber from the crystal space.
yes.
In general, yes, in general.
Yes, yes, yes.
And so, if I
Maybe I don't know.